Advanced reflection high energy electron diffraction, or RHEED technique, presented by Kyron B. McLean for EEN 650 in the summer 2024. RHEED stands for Reflection High Energy Electron Diffraction. It's a pivotal analytical tool in surface science. It utilizes high energy electrons, normally 10 to 100 kilo electron volts, incident at shallow angles to probe the surface atomic structure of crystalline materials. RHEED generates diffraction patterns that provide atomic scale insights into surface morphology and structural integrity. It is a key technique for studying surface phenomena, particularly in thin film and semiconductor research. Some of the key parts that we'll be discussing are the electron gun, which you see in the picture above, the sample holder, the sample detector. Let's delve into the fundamental principles and mechanisms of RHEED. First, we have the electron source. Electron gun generates a collimated beam of high-energy electrons, typically in the range of 10 to 100 kiloelectron volts. These electrons are directed towards the sample at a very shallow, glancing angle, usually less than 5 degrees, which optimizes surface sensitivity. Now, let's talk about the diffraction phenomenon. The Edwall sphere construction is a theoretical model used to visualize diffraction conditions in reciprocal space. The radius of the Edwall sphere corresponds to the wavelength of the electrons, which is crucial for understanding the diffraction process. In RHEED, we consider two main types of scattering: kinetic and dynamic. Kinetic scattering assumes that each electron is scattered only once by the surface atoms. This simplifies the interpretation of RHEED patterns, making it easier to analyze the surface structure. However, in reality, we often deal with dynamic scattering, where electrons undergo multiple scattering events within the crystal. While this complicates the diffraction pattern, it provides a more comprehensive surface analysis. The key to understanding these diffraction patterns lie in reciprocal space. Positions and intensities of the diffraction spots give us detailed information about the surface atomic arrangements, periodicities, and possible reconstructions. This analysis helps us understand the surface structure and dynamics at the atomic level. In summary, the operation of RHEED involves a very precise interplay of high-energy electron beams, shallow incident angles, and sophisticated pattern analysis to unravel the surface structures of crystalline materials. Here we have an illustration of our monolayer growth, or the surface that our RHEED technique will be measuring. If you notice in our second column, we have our different type of electron beams. Our first and fifth are kinetic, and our second, third, and fourth are dynamic. Our third column, we have our theta, or angle of the beam. And in our fourth column, we have our signal, the RHEED signal we'll be measuring. Now let's take a closer look at the advanced instrumentation setup used in RHEED. First, we have the high-energy electron gun, which is crucial for generating a highly focused, high-energy electron beam. Typically, these beams operate within the range of 10 to 100 kiloelectron volts, which allows us to achieve the necessary surface sensitivity. One of the critical components of this electron gun is the tungsten filament. Tungsten is chosen because of its high melting point and its efficiency in emitting electrons when heated through thermionic emission. Next, we have the precision sample holder. This component is essential for accurately positioning the crystalline sample at the required angle. Maintaining this precise angle is vital for the accuracy of our diffraction measurements. Additionally, the sample holder operates under ultra-high vacuum conditions to ensure that the sample remains clean and free from contamination. Moving on to the detection system, we have a phosphorus screen on a high-resolution detector to capture the diffraction patterns. This setup allows us to visualize the patterns with a high spatial resolution, making it easier to analyze the surface structure of the material. An ultra-high vacuum chamber is essential for RHEED experiments. The UHV environment minimizes electron scattering by the background gas to prevent contamination of the sample surface. To give you an idea of the required conditions, the electron energies of 10 kilo electron volts, we need to maintain a chamber pressure of 10 to negative 5 millibar or lower. This level of vacuum is necessary to prevent significant scattering of electrons, ensuring the accuracy of clarity of our diffraction data. In summary, the RHEED setup is a sophisticated arrangement of components, each playing a critical role in obtaining high-quality diffraction patterns and accurate surface analysis. One of the most critical applications is real-time monitoring of thin film growth. RHEED allows us to observe the growth process as it happens, ensuring that we can optimize the epitaxial growth process to achieve high-quality thin films. This real-time capability is essential for controlling film thickness, growth rates, and surface morphology. RHEED is also invaluable for studying surface reconstructions. Surface reconstructions refer to the rearrangements of surface atoms that differ from the bulk crystal structure. By analyzing RHEED patterns, we gain in-depth insight into the rearrangements, helping us understand the energetics and stability of the surface. Defect analysis is another significant application. RHEED enables us to precisely identify and characterize surface defects such as vacancies, dislocations, and step edges. This level of analysis is crucial for improving material properties and performance. In semiconductor manufacturing, RHEED plays a vital role in quality assurance. It ensures the structural integrity and quality of thin films, which is crucial for device performance. RHEED is extensively used in the production of high-performance electronic and optoelectronic devices, making it an indispensable tool in this industry. RHEED offers several key advantages that make it an essential tool in surface science. Firstly, RHEED provides exceptional surface sensitivity. It's ideal for detailed surface structure analysis, giving us high-resolution data on atomic arrangements and periodicities. Secondly, the real-time monitoring capabilities of RHEED are a major advantage. We can observe dynamic processes like film growth and surface reconstructions as they happen. This real-time insight allows us for precise control and optimization of these processes. Another significant advantage is that RHEED is a non-deconstructive characterization technique. It preserves the sample integrity while providing detailed structural information. This makes it suitable for continuous monitoring without damaging the sample. Finally, RHEED offers atomic scale resolution. It delivers precise information about atomic surface arrangements, which is essential for advanced materials research and development. This level of detail is crucial for understanding and controlling surface phenomena at the atomic level. While RHEED is a powerful technique, it does come with some limitations. Firstly, accurate RHEED analysis requires a crystalline, atomically smooth surface. Rough or amorphous surfaces can produce complex and uninterpretable diffraction patterns, making analysis pretty difficult. RHEED also provides information limited to surface structural analysis. It doesn't give us bulk properties, so we may need complementary techniques for a comprehensive material characterization. Also, the diffraction patterns produced by RHEED can be intricate and require substantial expertise for accurate interpretation. Multiple scattering effects, known as dynamic scattering, can complicate the analysis. And lastly, equipment costs for RHEED can be high. Advanced setup and maintenance requires significant investment, including ultra-high vacuum systems and high-precision instrumentation. These factors need to be considered when deciding to use RHEED for surface analysis. Let's look at a case study that highlights the practical application of RHEED, real-time monitoring of gallium arsenide epitaxial growth. The objective here was to utilize RHEED to monitor the growth dynamics of gallium arsenide thin films. This involves real-time observation of RHEED patterns to ensure smooth, defect-free epitaxial layer formation. By analyzing the evolution of these patterns, we can optimize the growth parameters. The results were impressive. We received high-quality gallium arsenide films with precise control over thickness and compositional uniformity. This case study demonstrates the critical role of RHEED in semiconductor fabrication. Providing real-time insights into the growth process, RHEED helps ensure optimal growth conditions and high-quality film production, which are essential for high-performance semiconductor devices. In conclusion, RHEED is an indispensable technique for advanced surface analysis in material science. It provides high-resolution, real-time data on surface structures and morphologies, making it integral to research and quality control in the semiconductor and thin film industries. Despite some limitations, such as the need for ultra-high vacuum conditions and complex pattern interpretation, the advantages of RHEED make it a crucial tool for specific high-precision applications. RHEED continues to encourage further advancements and innovations in materials characterization and thin film growth monitoring. Its ability to provide detailed, atomic-scale insights into surface phenomena assures its ongoing importance in advanced materials research and development.